Okay, we're just doing a bit of work here. I just want to share a project really on cell division. We're doing this in science, and we've done a little project. Perhaps I'll share that with you to start off here, because we've got just a scanning electron microscope picture of some brewer's yeast, I think, that I just got off the internet. And what we've got down here is a sourdough starter culture. So with my students, we had a look at yeast in another activity, and I'll just quickly show that to you. I called it Yeast Week, where again, there's the same picture there, but we looked at fermentation and making bread or pizza dough. I think that's where we stopped here was we looked at unleavened bread, so making flatbread and things like that. And I've got a little video there to show the students and talking about flours, and then another series of videos to make pizza dough. So when we get to this activity that I want to share with you now, they've had some hands-on experience with yeast and making dough. So we talk about, because they always ask, can we see the yeast under the microscope? And that's why I have that picture there, because using a light microscope, the answer is no. And just with this picture here, we can see all the gas bubbles here, and that helps reinforce this idea that the yeast are in there and they're active, and we see the bubbles of CO2, and we know that the yeasts are active and consuming the sugars and multiplying, because we want to look at cell division. So they've got that hands-on experience, and we just did a bit of work to reinforce a few ideas on microscopes, microscopic, and macroscopic. So that's where we're going to go with this project here. And I get them to think about how the yeasts are dividing, and quite quickly they work out that they're splitting in two. And I asked them to create a little simple scenario where we can model that, what happens if we started with one yeast in our pizza dough, and the yeasts were dividing every 30 minutes. How many yeasts would there be after 4 hours? So that's the kind of little setup that I had here, and you can see that in the students' work. They begin to explore what that looks like. And what's really interesting here, if I go down here a little bit, there's a really interesting piece of work here where the student has tried really hard here actually to map out each of those divisions. And what I'm hoping for is when we get to this, we don't quite get to this stage. A lot of people stop, and where's some examples here? They're stopping here, and then they're relying on the numbers, and that's a really important realization, if you like, that it gets messy after a while and time consuming and boring to be drawing these drawings like we've got here, where we know that they're dividing in two, and then we're doing our math, if you like. We're doing our math here. We're going from 1 to 2 to 4 to 8. And what's interesting, students realize that it's doubling with every 30 minutes. And so you can see again, there's examples here of how they're doing their maths. They're multiplying by 2. If they've stopped, they're multiplying by 2. This guy here, this student here, has done both ways, and I haven't even stopped to count up if there's 256 little circles on that last division. So there's something important that we want to model next. And because it's a binary system and we're splitting things in two, there's a really important teaching moment that we do here. We've gone from 1 to 2 to 4 to 8 to 16 perhaps. And because we're splitting in two, I show them that we can use a base 2 system. And what I find, a lot of students are pretty shaky with their index laws here. And there's a couple of really important teaching moments here. To anything to the power of 0, maybe I write it like this: a to the m equals 1. And when a to the 0, sorry, should put it like this: a to the 0 equals 1, and 2 to the power of 1 is just any number to the raised to the power of 1. It's just going to be that number again. So they're really important things that we can work on mathematically. And then what we can do then, and what I often said, and you can see that here with this last question here, I asked them to work out what 2 to the power of 25 is, just to check that they understand what that looks like and how they, using their calculators here, whether they can input that correctly into their calculator and get the right answer. And also, it's a really good reinforcement of, you know, the power of just splitting things in two. And what we tend to do next is, in this system here, we've got a model here, we begin to, I ask them to begin to model out what this situation looks like, where we've got time and we've got the number of yeast, the number of cells here. Now, I asked them, what does it actually look like? And is it a straight line or is it some kind of curve? And we plot a few points out, and we realized that it is a curve. And this doubling, this type of exponential growth, we can do that. So what's really interesting here is we can help refine our model, because I'm asking students what's happening. We've got, they understand, and I don't know if it's, I don't think they divide every 30 minutes, but 30 minutes is an important time block, because if we're watching the clock and we say 4 hours, students can model this quite easily once they understand to splitting twice every hour. We've got 4 hours, so it's going to be 2 to the power of 8, that's 56. So the kind of extension work that you can do is begin to refine this model mathematically. And you could perhaps do things like model this, I don't know, let's use the letter D for how many divisions in 1 hour times time. So this situation here, this question that I set them, we could model that as 2 to the power of, if it's dividing twice in 1 hour, and we let it run for 4 hours, you would end up with 2 to the power of 8, and that would be the same answer. Again, 2 to the power 8, I think it was 256, just might need to check that. We got 2 to the power of 8, 256. And just to show you here, like this is a teaching moment where you can teach students how to use their calculator a little bit more programmatically and set up the same thing. Okay. So they're the things that occur in the class based on their knowledge. It's really important, I think, that they go home and during Yeast Week and make these pizza dough for themselves, and they enjoy that because there's something to eat at the end of that. So this is interesting work here because we've got one cell splitting into three. Probably tells me this student's either made a mistake or didn't understand something. So where do I go next? That's important because we've done the microscopic work. Again, students can't see the yeast. They can only see that the yeast is doing its job and causing the dough to rise and form the bubbles. So that's where I tie this into a macroscopic type problem. So where I go next with this is we head outside and we try to use this on the trees outside at school. I like to pick trees that have lost their leaves, so we can just look at the branches and how the tree is branching. And I tell them this story here, and it's the same story I've got on the back of the screen behind me here. This book here, What's the Point of Maths, is a really good resource with a lot of really good projects in it. And the story here is about an Indian prince who, riding his elephant, points out to his servant that I think there's a certain number of leaves on this tree, and the servant or his companion doesn't believe him and then goes back and chops a tree down and counts all the leaves by hand, only to discover that the king has estimated the number of leaves on the tree quite accurately. So it's really that modeling situation that we need to get into, and we've done the work with the yeast and something we can't see that is branching and splitting in two. We're looking at the trees and they're branching, the branching pattern. We're just assuming that they're splitting in two, and most, depending on the tree that you choose, of course, most branching patterns are splitting in two, and we can model that using some of the knowledge that we've already discovered. And of course, we can set up a couple of models here. We can do it the King's way, where we can count the number of leaves and the number of twigs and the number of branches on the tree to get to arrive at a reasonable estimate. So that's one way of doing it, and then I try to ask them to, well, let's go on to generate a sensible answer. So then I ask them to use their knowledge on how to model this using assuming that the trees are splitting in two. So of course, it's an important moment to remind those students who want to be like the king's companion or servant or whoever it was that, no, we're not chopping down the trees. We're going to use a mathematical model to estimate this. And so this is this point, I've just got to introduce this book here. Carol Vorderman has got some really good resources for programming, and one of these here is making fractal trees, modeling what a tree looks like. And I've done that code, so I just might show you that quickly. And this is at this point something I show the students. Whoops, let's start that again. Let's start it again. Well, and this, the branching, the angles are a little bit randomized here, but certainly we can. It makes sense to use a binary model to model a tree, or these kind of look like broccolis or trees of doom or something. So with that in mind, then we step outside to model what's happening with some of the trees outside in the school grounds. So what's interesting here is that we're doing that job of estimating, and we've got two methods that we can look at here. And what I ask the students to do is look at one branch and see how many times that it splits. And we can model that as 2 to the power of 6, if you like, or whatever you estimate. And it's really interesting watching the students, you know, picking certain branches, and it's a good opportunity to talk about, well, what's an average looking branch on that tree, and how many branches there are in total, how many. It's interesting too, if you choose a tree in the middle of winter that's got no leaves on it, you can count up the buds on the end of the leaves and estimate the number of leaves there. So it's really interesting work that they're doing, and it's a messy situation where, because there's, and even though there's no leaves on the tree, we can sort of model it, and we know that we may not be right, but that's not important. We may not be right until the exact number of leaves. Now, what's interesting here, what do we got? We've got the number of leaves. So we might model that with an L, and we times that by the number of branches. So 2 to the power of, because each branch is splitting in 2 in our model, let's call that 2 to the power of B, times how many branches in main branches in total. So this is our model. How are we going to do this? We're just going to call that M for main branches. And the final bit of work here is really interesting, because this is what I asked the students to do next, is which one of these variables is going to be the most critical in your answer. It's easy. They find they can count up this quite accurately, the main branches of the trees, and they're using some knowledge of average here to look at the average. And this is easy if we just look on the buds on the end of the terminal branches here, and we start counting those up. So we can get again an average, but quite an accurate average. And that's interesting. And this is what this student over here is playing with. He's thinking about what happens if I change the number of leaves? And yes, it does make a difference to the model, but the real action in this model, and the biggest source of error, comes from this middle bit here, which is really interesting, and watching students play around with this. If they choose, say it branches 3 times versus branching 4 times, well, because this is a binary thing and it's doubling, this will double every time we increase the power. And if we're wrong on this one, we could be 50% out on our answer. So this part of our mathematical model becomes a critical thing to get right. And there's an extension to this too, like depending on the type of trees that you've got. Here we go, we've just got the tree here. You might find that all the leaves are up in the canopy. And so if you count, say, let's do this, we might have 8 branches, and only the last 3 branches have the leaves. So we could actually improve our models slightly to estimate the number of leaves correctly or better or more accurately, and then multiply them by the number of leaves and on each branch and how many main branches there are in total. So they're little improvements that we can make, and they're interesting things to talk to students about as they're out in the yard modeling what is a messy problem, a real world problem. And there's 2 extensions to this, and it's a nice little journey to take it. If I go back to the very start here, take it from figuring out what's happening in your pizza dough or your sourdough starter for your bread here, and then expanding that knowledge up and connecting with something very similar on a much larger scale, trying to take this century-old story and centuries old, I guess, to you know, look at this kind of thing where we're modeling the leaves on the end of on the tree. So I find this is a really good project. There's a lot of really good learning, and there's a lot of really good, oh, now I understand how it all works, and tie in a lot of maths and science type ideas. So I hope you enjoy running a similar sort of project. Thank you.